Let's start with just what is a big picture overview of the course. So I'll tell you, this is my absolute favorite course to teach. I've taught a lot, but this has emerged as the one I love the most. One of the things I love about the course, there are kind of two extreme perspectives that we can look at. We'll talk about what those are in a moment. But let's just talk about what does discrete structures mean. So I'm going to ask you, if you would, to just take a moment and think about if you know anything about either of these words. And then as you're thinking about that, consider if you'd be willing to share your ideas about what these things mean. There's the word discrete, discreet, that means hidden. And there's a word discrete here. So like if you can trust someone with a secret, they're a discrete person. But this is a different word. Although it turns out that that's really connected, because one of the things I love about discrete math is that it's connected to cryptography. Cryptography is the math that is used to keep important information secret. So you may have heard of cryptocurrency. Cryptocurrency is built on cryptography. What else do you know about discrete? So discrete means here that you don't have anything between. There's some like set distance and you can't get any closer. That's not the case in calculus, right? So in the real numbers, you can get anything you want. You can take a limit. You can get closer and closer and closer. And basically things are, you can just keep getting closer and closer and closer. Like there's no smallest positive real number. And of course that's nonsense. We don't want to deal with that. So we're only going to deal with things that have a certain separation between them. Usually we're going to be working with the positive integers or the natural numbers. I can't think about 1/2 when I'm in discrete world. It's either 0 or it's 1 and there's nothing in between. Or it's 4 or it's 5 and there's nothing in between. Now, why is this interesting? Well, calculus is what we use for the physical world. Calculate velocity. We can think about a car moving in a road or in space, or an object moving in space. This type of math is what we use in the computational world. So the structures that people create, calendars, schedules, committee assignment, you can't be on like 3.5 committees. You're either on 3 committees or 4 committees. So when you think about anything that involves labeling or assigning or creating a structure, usually the human-made structures are discrete structures. When I just say structure, what do you think? Framework? What do you mean by that? Okay, so like a skeleton of a house. That's certainly something I would want to have a clear structure. You better not try to build my house out of Jello. Although Jello is a structure, but it's not the kind of structure we want. We want something that's clear and strong. Something that's built. What's something that could be built that you would think of as having a clear structure? A bridge. You're thinking of physical things, and that's normal because we tend to think of physical things first. So these are definitely examples of structures, and they're really cool to have in our mind. An example of a discrete structure would be something that's like this, but that is created in a way purely information. So for instance, the schedule of university classes, that needs to have a really clear structure. So the assignment of classes to rooms at particular time is a discrete structure. Now these are the two words we're going to be looking at. And there are kind of two perspectives on discrete structures. There's the algorithmic CS side of these really hard computational problems and how do you attack. So how many of you have ever watched something because Netflix suggested that you should? One person. Okay, I admire everyone else's moral judgment. Good for y'all, individuals. The Netflix recommendation algorithm is an example of a discrete structure. And if you think about it, it's working with really big data sets and it's really sophisticated. Actually, I would say every algorithm you can think of would fall under the rubric of a discrete structure, even if it's working with continuous things in some way that the time steps are going to be discrete at least. And usually there's some kind of data structure that's discrete underlying. So these are usually really hard, like the math that protects your debit card information is built on a discrete structure. And then how do you say this? The playful side, where maybe things aren't as serious. Have you ever played with the Rubik's Cube? It's a discrete structure. Have you ever played 20 questions, the guessing game? That's a discrete structure. Lots and lots of mathematical games and puzzles. Have you ever done that really annoying golf tee hopping game at Cracker Barrel? That's a discrete structure. But we want to start with simple questions, and then we want to gradually explore and let the complication emerge. And this is partially because of how the class is laid out. This is partially about like the nature of discrete structures. And also this is partially about how I personally like to look at things. We could start with the most complex notation and the most complex problems and then try to break them down. But I don't see the point. My goal when I'm teaching is that for almost all of the class, almost everyone should understand what I'm saying. So that when you leave to explore on your own, you are starting from a clear place.